All right, well, it is almost 1 o'clock here, and I do want to just go ahead and welcome everybody to the OpenXLR8 webinar that we're doing this week. This is one that we've been really excited to do for some time, and as a little bit of background on this, this is really largely based on a hands-on tutorial that Brian Craker and I did out in California last month in December. We were part of the Embedded Systems Conference, and so we did that webinar, or we did a hands-on tutorial. It was a 2-hour session that we did out in California as part of that. It was a really cool thing. We had about 30 people show up, and it was a hands-on tutorial, so we actually gave away XLR8 boards, and people came, a handful came kind of prepared to step through with us, and so we were able to walk them through this entire process, and we had probably about 4 or 5 groups of people that were able to get through this entire process in 2 hours. So what we've done today is we originally scheduled this webinar for 1.5 hours. And I don't know that it's going to necessarily take us that long to get through everything, but we wanted to leave enough room to be able to make sure we can kind of pause a little bit, and so we can answer a few questions as we're going along. And there's a lot that we're going to be doing here as we step through code and through different tools and things like that. So it's going to have a lot more of a sort of technical tutorial feel to it than sort of a standard webinar. And so I hope it's going to be a great experience for you guys. Again, my name is Jason Pecor, and I just want to kind of introduce ourselves a little bit. So I'm going to be joined today by Brian Craker, who's one of our hardware and software engineers here on this side. He's been doing a lot of the work with us on XLR8, and he's the one that joined me in California last week. And then also by Harley Judes, and Harley is sort of running stuff in the background with the webinar and going to be answering some of the questions and posting some of the links that you guys have or that we have to share with you, and handles a lot of our digital marketing and things that you see in terms of our presence out there in the world. So it's going to be Harley and Brian and I, and we're just really glad that everybody is here. Now, a couple of quick housekeeping notes. As usual, everybody's in mute mode right now. And so if you have questions, there is a question box there as part of the GoToWebinar interface. Go ahead and ask those as they come up and as we're stepping through this, because we'll be able to answer them sort of in real time, either with typing back to you or by just speaking directly to it as we see those questions come up. So don't feel like you need to wait till the end. Go ahead and ask real time, and we'll just address those as we're moving forward with this stuff. And a couple of other notes. We have noticed in the webinar we did last week and in some of the things we've seen this week, we've seen some sort of network latency outside of our offices. And so if you guys are experiencing some kind of audio degradation or something like that, please speak up. We just want to be aware of it. I'm not sure there's a whole lot we can do to control it, but we want to make sure that you guys have a good experience here, and we just want to get some sort of real-time feedback if you see any of those issues as we go along. So let's back up real quick to what we're going to be doing today. And while I talk about this, I want to first start by having a few polls that Harley puts up there. And we're just doing this because we want to get a sense of the demographics of the people that are on the call. So go ahead, Harley, and throw the first one up there for us. And what we want to get an idea of is, one, just sort of your experience with XLR8. So if you can just go ahead and answer that real quick. It gives us an idea, either you have one, you've heard of it, or you've never heard of it before. I suspect most of us will fall into, you know, the top 2 categories. Okay, so we've got several people. Most people here are familiar with our XLR8, either they own one or they've heard of it before. And you can go ahead, as soon as that's done, Harley, and share. You know, go ahead and share where we are right now. I think it's pretty representative, so people can kind of see, you have some idea of how the poll results came out. So most of you guys are familiar with it. That gives us an idea of how much we want to dive into what XLR8 is. And go ahead and grab the next one. We kind of want to get a feel for where people are with an experience of, in terms of using FPGAs. All right, so let's go ahead and get rolling. What we're going to be doing today is we're going to be walking you through this process that we have called OpenXLR8, and we're going to be taking a piece of code and taking it through the whole process live and demonstrating going through the tools. Now, if you have a board with you and you are planning to use it and walk along with us, first, I think that's awesome if you've come kind of you got your tools set up. But I want to let you know that if you bump into some challenges in this format, we're probably not going to be able to help you step through those challenges and overcome those hurdles. like I said, we'll be sticking around. We scheduled this for 90 minutes, so if you want to stick around afterwards, if you're trying to follow through and follow along, we can help you get over the hump on that if you get locked up or hit some kind of roadblock. I mentioned this, some of you may have missed early before we just kind of were telling people, one of the things that you're going to need to do if you want to follow along or later on, and you'll be able to get this because we'll make all this presentation available for you and indeed even a replay of this webinar at a later time, you're going to want to go out to our GitHub repository and grab this Accelerate LFSR block. Now this is a block that Brian has designed that you can use as a standalone XB. It's a great starting place to kind of learn this process. And Harley has posted that link in the chat window. The thing you're going to want to do when we actually go through this process, and we'll come back to this rationale on this again, is that you're going to want to download that zip file from GitHub, and then after you expand it, rename it to Accelerate Build, and move that to your Arduino libraries directory. And because the way that we've set up OpenXLR8 to work to kind of make everything easy for our users, it needs to be there under the Arduino libraries folder. So once you download that, and we'll come back to this again too, and so this isn't the first time you'll see this or the only time you'll see it as part of this webinar. And finally, at the bottom of this slide, you can see the address for the URL for our Arduino boards. And I'm sorry, our board library URL to go into the Arduino IDE, and that'll become important because when we move into actually putting the sketch in and compiling it and uploading to our board, we're going to need this to be able to add some of the packages that we require. This is also in the chat window. Harley has put that link out there. We will address this again, but if you are, a lot of you are familiar with Accelerate and you're familiar presumably then with using the Arduino IDE, one of the things that we're going to need to do, and we're just going to talk about this real quick, and we'll come back to it later when Brian is talking, is we're going to need to go to our managed libraries, and there's two libraries that you're going to need, and one is Accelerate Core, and the other one is Accelerate Build Template. And so we'll come back around to that momentarily, but this is an important piece for getting it actually running with the Arduino IDE a little bit later on. And Brian will actually demonstrate where those are and how we find them. Just wanted to give you the rationale behind needing those board URLs for right now. So let's kind of jump into a quick overview at a high level of where we going today, and then I'm going to turn things over to Brian, and we're actually let Brian just kind of step through it as we go through the different tools. So most of you on the call today are familiar with what Accelerate is, and so I'm not going to spend a lot of time on this slide, but there are a few people here that are not, and so I want to talk about this just real quick. So what we've done with Accelerate is essentially a clone of an Arduino Uno, but we did something a little different with this. Instead of putting the standard 8-bit microcontroller from Atmel on our board, we actually have an Intel Max 10 FPGA, and this is an FPGA. What an FPGA, if you're not familiar with that, stands for Field Programmable Gate Array, and it's essentially a custom reprogrammable hardware piece or chip or piece of hardware that you can write your own custom hardware for. And then you can reprogram that. And their FPGAs are great because you can do your own custom thing, you can make changes in the field, and it doesn't just have to stay with that one functionality. But what it brings to the table over a standard microcontroller or other chips is it can be very, very high performance compared to running things in software on a standard microcontroller. And so what we wanted to do was sort of bring the power of that FPGA performance to the Arduino platform, and that's what we're doing with Accelerate. The cool thing that we did as well, though, is very often when you're designing FPGAs, you do need to have some special tools to do it, and you need to be able to have some additional hardware to actually program these things. And for the base level, the sort of fundamental functionality of Accelerate, you don't need those special tools and you don't need the special hardware. You can just use the Arduino IDE as you're used to using it, and you can even program it with that, even in terms of configuring some of the sort of custom things that exist on the FPGA. So our goal from the beginning was to provide an Arduino type of platform that had the high performance capabilities of an FPGA for those users who were using Arduino for some application but were bumping into some performance bottlenecks and wanted to just see improved hardware performance, or for people who want to learn how to use FPGAs. This is a great environment, and that was really the focus of our ESC talk in December, was people who are embedded designers, who are familiar with Arduino, who want to kind of take that next step in designing FPGAs, this is a great platform for that because we've provided a mechanism that allows you to just start by designing a small block and then pulling that in to the FPGA sitting on our Accelerate board and still taking advantage of it using a regular Arduino sketch or a sketch that you're running on our board in such a way that it doesn't require you to design the entire FPGA from scratch. And that's a really powerful thing for people who want to learn how to do these. So the question might be, well, why would I want to use an FPGA? Why would I want to design my own block for the FPGA in the first place? Well, the first reason is because you may want to run that functionality faster. When we talk about this, we're talking about acceleration. And so if you take a function that's running in software, that's, let's say you're running on a microcontroller or some other type of small CPU, just about any time you can take that functionality and migrate that to some kind of custom hardware implementation, you are going to experience a tremendous amount of acceleration, and you're going to be able to run that way faster than you can running on an instruction-based processor. And sometimes we're even talking about orders of magnitude type of improvements for certain applications. So it's significant what you can experience in terms of improvement on hardware that's designed custom for running that function. That's why, you know, people design ASICs. That's why people design very custom chips to do very special things like network processors and search engines and all kinds of custom functionality, because you just get that much more performance out of it when you run it in hardware. In addition to that, you get a higher performance overall solution. And at first glance, you might think, well, higher performance sounds like faster. Isn't that the same thing? And it's really not. I mean, it's related, but what you get when you move things into hardware or you run it on an FPGA is you get this notion of offload from the processor itself. And this is something Brian will actually demonstrate pretty well with some statistics a little bit later, is that if you can take that functionality, particularly if it's burdensome to the microcontroller or to the processor core, and then now you can push that onto some custom hardware, now you're talking about freeing up that processor again to do other things. So there's a lot of functions, there's a lot of tasks that can just run nicely all by themselves out in their own custom hardware space on that FPGA and interact very little with the actual microcontroller itself. So that frees up that microcontroller to just do whatever it wants to do, and it allows that offload to take place. So those are really the two primary reasons why, if you're sitting here thinking, well, why would I care about doing this? Why would I want to use an FPGA? This is it. You can speed up what you're trying to do, and you can offload the processor in order to be able to free it up to do other things. So here's what we're looking at doing today, and we're going to take and what would normally be running on, we're going to show an example of a sketch that we're going to be running on the microcontroller, and then we're going to design some logic and move it down here to this area that we've got for the accelerator blocks. And for those of you new to FPGA, or to Accelerate, I'm sorry, this is basically what the block diagram looks like inside of our FPGA. So up at the top, we've got the AVR instruction set compatible microcontroller that we've designed. So we've got the microcontroller that we designed, which will run all your standard Arduino sketches and behave just like a 328, ATmega 328 microcontroller. And the rest of the FPGA we've left open for this programmable accelerator blocks. And by standard, or by default, when we ship, we have a set number of accelerator blocks that we send out as part of the package. But this area is there for you to be able to customize as well, and that's what OpenXLR8 is all about. So talking just a little bit deeper about accelerator blocks, because we're going to be talking about how to design your own, what we're talking about here is essentially a custom piece of hardware that's going to be sitting in that section that's dedicated for the custom FPGA stuff. It's very tightly integrated with the microcontroller. So the XBs themselves, the accelerator blocks, can access that same register space as the microcontroller and be integrated right with the instructions. In fact, that's how our XBs work, is we have an instruction and a register space in between the XBs and in between the microcontroller, and that's how the microcontroller can talk to that custom functionality that's living out there on the FPGA. But this is just the term that we use to define an optimized hardware implementation of any given function that you want to speed up or that you want to put in the custom hardware. And if you look on the left-hand side here, you'll see that the accelerator blocks that we currently have are floating point math, servo control, NeoPixel control, and enhanced analog to digital functionality. on our roadmap, there are a handful of things that we see coming down the road that we've been asked to do. And these three in particular came up recently: quadrature encoder, pulse width or PWMs, as well as PID control, is something that has come up recently in conversations with customer. And so we are currently working on the quadrature encoder side of it. We're kind of actually talking about PWMs because the servo control that we've got is a special case of a PWM, and most of our customers are using pulse width modulation for controlling motors and servos, and so that one might be backed up just a little bit. But PID control is integrated in with that robotic space as well, so that's something that's earlier in the timeline for what we want to develop. But that quadrature encoder is very close to being done, and as soon as that's ready, we'll make sure we let all of our customers know about that. So how do you get your own custom accelerator block on the FPGA or on the XLR8? Well, that's where this OpenXLR8 methodology comes in. And this is something that we designed to allow you to be able to design your own custom accelerator block and put them onto XLR8. So what we're going to do today is we're going to do just that. And I want to fly at a really high level here as we're getting ready to have Brian actually step through the process, because I want you to be able to get conceptually the idea of what we're doing, and then we'll kind of step back into some of these images as we walk through the process and make sure things make sense. And I'll say this too, we're going to throw a lot at you during this webinar. So we're going to be jumping between code to different tools and back to presentation stuff. And we don't necessarily expect that coming out of this webinar you will immediately just be able to go right through the process again and have it done no problem, because there are quite a few steps in here. But I think what you'll see is that even though there's a few different steps, it really is it's a pretty easy way to get your custom stuff running on this board that then you can access just like a standard Arduino. It's really cool. So we're going to start with this LFSR block. So an LFSR is a linear feedback shift register, and it's just one way to generate a pseudo-random number generator. It's a specific kind of circuit that we will be looking at a little bit more closely as Brian shows you in the code. So we're going to take a look at this Alorium LFSR.v Verilog block. And then what we're going to do is we're actually going to wrap it in the LFSR Testbench. And this will allow us to test this module standalone. So we're going to pull that module into ModelSim and run a simulation. And you'll be able to get an idea of, okay, we're going to drive this, we're going to be able to look at the outputs, and at least get an initial look at what it looks like to simulate this at the block level. From there, we're going to take that LFSR block and we're going to wrap it with this XLR8 LFSR wrapper. And we'll talk a little bit about how that kind of positions that block and gets it ready to be hooked into XLR8 at the top level, which will be the next thing we do. So we've taken our core LFSR Verilog block, we wrap it and prepare it with some of the signaling and stuff it needs to be hooked into the top level, and then we're going to wire that into the top level Verilog. And inside of that XLR8 top, there's a handful of other components that are in there for, the program memory, data memory, handling GPIO, the actual AVR core is in there, and Brian will talk a little bit about kind of where all that stuff lives. We're not going to get into the super details about everything of how XLR8 top is architected. That's just not, really doesn't fit into the scope of what we're talking about today, but enough to understand kind of where things live and how it needs to get wired in. From there, we're going to take the XLR8 top and actually run it through Quartus Prime. So this is Intel's tool that we can use to synthesize our core, and we'll dump out a programming file. Now, one of the questions you might be asking yourself, both with ModelSim, which is a mentor graphics tool, and with Intel's Quartus Prime, is, geez, aren't those tools kind of expensive? Well, the answer is yes, they can be. But the cool thing is that our code and our design is small enough that you can do this using their free versions of their tools. And so both with ModelSim and especially with Quartus Prime, these are actually extremely powerful design tools, FPGA design tools and simulation tools that you can download and use for free, and our code will run through that. So there's no expense to you for buying these tools to do it. There's some expense in terms of doing the installation and getting everything running, because it takes a while to do that side of it. But once they're in, we can use those, and it's really great. So really powerful tools at your disposal here, and we'll be walking through that. One step that we can do that we're not going to do today, though, is we've also built in the ability to simulate the entire design. So we can, for those of you who are really savvy with ModelSim and with doing FPGA simulations and things like that, we can actually dump out and simulate the entire XLR8 Top. So if you've designed an XB and you want to see how it performs in simulation before you run it in hardware, that is an option that you can do. But we don't have time for that today. Finally, we're going to upload that output of that synthesis file to the FPGA, and again, we're going to do that with Arduino. So those of you familiar with FPGA design, especially with Altera or now Intel FPGAs, that you have to have a USB blaster and program through the JTAG port, that's not the path that's required for OpenXLR8. We can program it right with the Arduino tool through the USB connector. So again, something that we're trying to make as easy as possible for our users. And then the last thing we're going to do is we're actually going to run a sketch. So Brian has put together a couple of example sketches using LFSR, the LFSR block, and both in terms of there's a couple different ways we can use it. And he'll show you what the libraries look like, and we're going to actually run it after we've uploaded it to XLR8, so you can now see that hardware running on the design. So that's the 1,000-foot view of where we're headed. I am done talking for a little while, and I'm just going to go ahead and shut down my desk sharing here. I'm going to let Brian take over, and we'll let him take it from there. So take it away, Brian.
All right. Okay, so we're the linear feedback shift register that we're creating today. It's this 4-tap LFSR, and we've chosen this polynomial. It's chosen it pretty arbitrarily, but we're tapping out at bits 7, 5, 4, and 3. You would be able to change this if you wanted to in the design and see the effect of that. But just for reference, this is what we'll be seeing today. So the first thing I'm going to do, I've created the LFSR in software for the Arduino. So I'm going to pull that up right here. This is my Arduino sketch that implements the LFSR functionality. So here is the function that does the actual LFSR calculation. So I'm taking in some seed value and I'm grabbing those 4 bits and XNORing it, and I shift the lower 7 bits of the LFSR up and append the feedback bit to the end of it.
Brian, can you jump back to the diagram of that circuit real quick?
Sure.
For people who haven't seen that before, it might be valuable. That kind of makes sense. So if you look at that assign statement at the bottom there is actually a Verilog, piece of Verilog code. That's what the actual final assign. We'll see that show up again in the Verilog for this. But there are a few ways you can implement these feedback shift registers. And in this particular case, we are using what's called an XNOR implementation. So we've got these tap points off from 3, 4, 5, and 7 on these registers, and that's feeding into a big exclusive OR and then getting inverted and fed back into the beginning of the chain. And there's nothing magical about 3, 4, 5, and 7 in this particular case. It was sort of random. There's an entire science behind how to pick tap points, and it has to do with how wide your register is, and where you pick these tap points will change sort of the sequence of numbers that you get out of it. And LFSRs, though, are very handy for being able to get predictable strings or sequences of numbers. And so they're used a lot. So for example, in verification or testing for chips, a lot of the stimulus generation is using these LFSRs kind of under the hood to generate pseudo-random numbers. And the cool thing about it, and you heard Brian refer to the seed value, is you can start off with a specific seed, so however you fix these registers at reset time, and you'll get the same sequence of numbers every time from a given seed. So it's very powerful from being able to predict a string of numbers and generate kind of a pseudo-random string. But I just want a little more time for your eyes to be able to look at this a little bit, and this is really depicting what it would look like in hardware with flip-flops or registers kind of feeding back into the entry point. And just wanted to call your attention to that as he's been talking about the code.
Okay. So down in my, I have my setup function in Arduino like we always do, and I'm starting the serial output so I can actually see the values. I'll pull up the serial monitor once I start it. I'm giving it some initial seed value. I'm just choosing a hex value of 55 and initializing the feedback bit to 0. And then in the loop down here, all I'm doing is I'm calling this advanced LFSR function over and over and setting it, whatever result I get from the advanced LFSR, I'm then storing in the LFSR data value, and I'm printing it out once every second. So I have this delay of 1,000 milliseconds, so it just will keep printing it out to the screen. So I'm going to go ahead and upload and run this on my Accelerate board here. So this will take just a second to compile and load.
And to be clear, right, this is just an LFSR implemented strictly as software in an Arduino sketch. So right now it's not using the hardware, it's not using an XB or any of the benefits of the FPGA. This is just, if you were going to run it, you could run this code on a standard Arduino board and it would just run, correct?
Right. This is, yep, this is 100% software and it will run on any Arduino architecture board. So
Okay.
So here I'm displaying the output once every second. I'm just outputting the LFSR, and we can see every second it shifts the 7 bits towards the top, and then outputs or it appends the feedback bit to the end, and I'm outputting the result. So that's pretty simple. And what I've done also, I've taken the compiled assembly code. And this is the resulting assembly code on the right here. So when you compile this sketch, the function that controls the LFSR is this line of assembly code instructions. So just something to keep in mind. It's every time we advance the LFSR, it steps through all of these memory reads and writes and math functions.
And we'll come back later, and the reason that Brian called that out is later on, after we demonstrate or run it with the hardware, we'll be able to compare and you get an appreciation for the change when you're running it out.
Okay, so now we're going to get started with creating the LFSR in RTL to put onto the FPGA. So I'm going to bring up the LFSR module itself. And here it is, Alorium LFSR is what we called it. And so this module, it contains the clock and reset that you need to advance the LFSR. It has an input for new seed to alert the LFSR module that you have a new seed that you want to feed into it. It has an enable bit so that you can enable the LFSR. So with that enable bit, you can either have it enable at certain points, like you can control when the LFSR advances, or if you leave enable high, it will advance continuously every time the clock input ticks. The seed input is how the user sends in the initial seed value, and then the output here is the actual LFSR data. So this is what the user will read back on from the LFSR block. Down here, we're declaring the internal wire of the feedback bit, and we have the statement here. We've seen this once already, but we're assigning the feedback bit to the XNORed value of those 4 bits of the LFSR data value. And down here in this always block, this is where the every time the clock ticks forward, it will enter this always block and will set the LFSR data value. So we have a reset call here, so that we're populating the LFSR data value with something on initial reset. And if we see a new seed value come in, we're going to set the LFSR data value to the user inputted seed value. We also have a catch here We don't want the LFSR data register to be set to all ones. Otherwise, the XNOR calculation will, it will always come out as a 1, and then we won't ever see data change. So we're just enforcing that in this statement here. And then the normal function here is that if the LFSR enable bit is set, it's going to grab the lower 7 bits of the LFSR data and append the single feedback bit to those 7 bits, and then save those 8 bits into the LFSR data, and that will be the new value of LFSR data.
And we certainly don't expect that, especially if this is new to you in terms of looking at Verilog code, that this is immediately going to make sense. But it's like looking at any new language. It may look a little foreign. I think, though, even not necessarily understanding Verilog, you can see that there really isn't much code here. And that's one of the things that we're trying to highlight. Again, this is a very simple example. Verilog code can get incredibly complex, just like any other programming language. But this is really a relatively simple block that ends up resulting in some very powerful results. But I can understand that it might be a little different. Well, all this stuff will be available to you guys. You'll be able to see it and download later and get more information on it.
Right. Okay, so now that we have our LFSR block, we want to test it in ModelSim so that we can actually see that that it works the way that we expect it to. So we have a Testbench available for it, Alorium LFSR TB for Testbench, and this is just a very simple instantiation and a file that will run the LFSR module. So in this file, we're including Alorium LFSR, and we're creating some local variables: clock reset, new seed, and enable, and the input value and the output value. And then this initial begin block, this runs right away when the program compiles, and it will run through until the end of it, where I have this call to stop, where it will stop executing. So so I'm initializing the clock reset, seed, and enable values. I'm setting reset low and then high again, and I'm giving the LFSR an initial value here of 10101010. I'm setting the new seed value high so that the LFSR block knows there is a new seed to grab, and then I'm toggling the enable pin a few times so that we can see the LFSR advance. Down here in this always block, this is a very simple clock implementation. I'm just I'm over and over, I'm just setting the clock value to the inverse of whatever value is currently at clock. So it will set high and then low and then high and then low continuously. And then down here, this is the instantiation of the LFSR module itself, where I am feeding in the local values for clock reset, seed, enable, input, and output.
And Brian, could you touch base real quick on, for some people, that pound delay might be new. It may look like, for a lot of languages, that hash is a comment, right? So if you could just touch on that, because that's probably new nomenclature for people.
Right, and that pound followed by a number, that's in Verilog, that's a call to time. So in a hardware description language, everything happens simultaneously unless you are telling something to consume time. So so I'm just telling the program to wait for 5 ticks, and those ticks, I believe, in default in Verilog happen to be in nanoseconds, I think, but I could be wrong about that. It's just so it's just my clock signal happens every 5 ticks, so you'll see clock go high and then low and then high and then low. So you'll see that everything happens on the 5-tick beat here. So everything is either 5 or 10 or 15, some multiple of 5, so that it follows the clock signal. So
now you're doing a very low level, very sequential stepping through. So from a test bench perspective, again, this is very basic, but we want to be able to demonstrate, and you'll be able to see when he actually runs it, how these pound delays result in signal switching.
Right. Okay, so now that we've seen our test bench, we're going to actually load the test bench into ModelSim and show it simulating. So we want to start up ModelSim, which I've done already. So here is ModelSim, and we want to create a new library in ModelSim. And by default, you're going to call the library the work library. I've already created this previously, so I'm not going to step through all of the steps here, but you're going to create a new library named work, and we're going to put it inside of the directory that holds our LFSR module and test bench. And then we're going to go up into compile. Oops. And we're going to go into, so again, those files that we want exist under the Arduino directory, under your documents and inside of libraries. The LFSR module already exists under XLR8 build here. That was a step that we went through previously, and we'll reiterate that a couple more times probably. So down into the RTL directory, here's that Alorium LFSR and that Alorium LFSR TB. We want to select both of those at the same time, and we click on compile to compile it into our work library, and I've actually done that already. So again, I'm going to not hit compile, but normally you just hit compile, and that will create your work library. And if you click the plus sign next to it, you'll see those two files show up here. So now you want to open up the test bench and open it up into the work area. So you do that by just double-clicking on the Alorium LFSR test bench, and ModelSim will load it. Takes just a second. Okay, and all right, great. Now to see that, we want to bring up a wave viewer. So if you select up at the top of your window, you select View and then go down to Wave. That's going to bring up a wave window. And we want to grab all of our signals. We actually want to see everything, every single one of these signals here. So I'm going to grab all of them and add them to the wave. Great. So here they all are, ready to go. Now we want to actually simulate the test bench. So we've got our waves into the wave viewer, and we want to go up here, and there is a run all button. Looks just like this. So I'm going to hit run all, and it's going to step through the commands that I've given the test bench, and I'm actually going to hit zoom full here too. There's a button that will spread out the waves so that you can see them a little bit better. So these are, here we can see the signals. Like as we step through the test bench, here's everything that I told it to do. So we can see first, here's our clock signal, and this, like I said before, it just sets clock high and low and high and low just at a constant rate. Our reset signal, we are toggling reset, and then we're setting a new seed value to give the LFSR block an initial seed, and then we are toggling the enable bit a few times. So here's the input value. I fed in this 10101010, and then I set the new seed bit here, and here we can see when the enable bit is set, we're actually able to see the output value for the LFSR tick forward. So it's a little bit hard to see it on here, but if you open it up in your own ModelSim window, you'd be able to see it a little bit better. That every time clock and enable are both high, it's going to tick forward by 1. So here it's grabbing that lower 7 bits and appending the 1 feedback bit to the end of it, and here it's happening again. So this is when I'm manually controlling the enable bit. And another important thing to notice here, when I set the enable bit to high and then leave it high, the LFSR output value is going to change with every clock tick. So here we can see that the LFSR value changes every clock tick. So
Brian, are you able to change the radix on that output real quick so it's decimal? It makes it a little more obvious. And then another thing I'll say too, as he's doing that, is that if these tools, there's a lot going on. There are tons of buttons and lots of windows and lots of options. As I said kind of in the beginning, these are extremely powerful tools. And so there's a lot of things they can do, and most of the time, particularly doing some of this stuff like this, it takes a little while to sort of get your bearings. But then there's a relatively small subset of things that you'll probably end up using if you're kind of new to it. So there'll be some amount of finding your way through it, but then you don't need to worry about lots and lots of it. And a lot of like all the buttons we're seeing here just allow you to be able to debug your output wave files easier, to be able to step through simulations and things like that. But don't be completely overwhelmed by how much there is here. There's a lot these tools can do. You don't need to worry about too much of it for doing just some of the basic simulation. And so as Brian switched, now you can see instead of looking at that output in binary form, it makes it a little easier in those smaller, like when it's changing on the right half of the simulation every clock cycle, you can see that you're getting a different value every time. And in this case, it happens to be a signed value, so we're getting some negatives. You could also change it to be unsigned. And again, if you're looking for sort of a pseudo-random number pattern to use for one thing or the other, that's a very valuable thing to be able to generate these numbers with a relatively simple piece of code.
right.
Yeah, thanks, Brian.
Yep. Okay, so we've seen now that's a pretty simple overview on how to simulate your own code. So so the next thing we're going to do is we actually want to bring this code into the XLR8 board. So we have more steps to go through to do that. We need to create a wrapper around the Alorium LFSR block. We're going to give it some communication hooks so that it's able to talk to the Accelerate board itself.
Hey, Brian, I'm going to interject real quick again. I apologize for the interruption, but before we move on from the simulation, I just want to make one point, and that is that the value of being able to do this is huge. So if you're looking at designing some custom piece of functionality, it's really great, especially once you get comfortable with using these simulation tools, to be able to see what your code is doing before you're actually running it on hardware. So you design this block and you set up a small test bench, even if it's really simple like this. You can look at all the internals of your code, and there's not many here in this case, but you can dive way down deep into your code and look at every every single signal that's there, and figure out why something isn't working the way you'd expect it before you actually have it on hardware on a bench. Because sometimes the things that don't work are buried way down inside that code, and it's really not clear if you're just measuring something at the outputs of a physical I/O pin, or it's not controlling a motor correctly. And to be able to look at it this level is extremely valuable in debugging your hardware before you're trying to do something in the actual lab or running it on a benchtop. So that's one of the real values of doing this. And I apologize, Brian, for the interruption. I just want to make sure I mentioned that.
Yep, sure. Okay, so now we're going to get into the Accelerate LFSR wrapper. So again, this is sort of how we communicate with the Accelerate board itself. The wrapper is going to essentially be controlling the register access for for the LFSR module. So basically any RTL design you have, it has registers associated with it, and you need some way to control that. So I'll talk real quick too about the different registers I'm using for the LFSR. I've implemented this using three registers, three 8-bit registers. So I have this LFSR control register, and that's a register that's mostly unused. The only bit that I happen to be using in the control register is a bit that controls free running mode on the LFSR. So that it's controlling the enable bit under the hood. So if you set it to 0, it's only going to advance the LFSR every time you read back the LFSR. If you set free running mode to true, it's going to update the LFSR every time the clock ticks. And then there's the LFSR seed register. This is a read-writable register, and this is where the user would input their initial seed value. And the LFSR data register, this is a read-only register. This is after the LFSR module calculates an LFSR result. It's going to store it here for the user to read back. And now the register addresses that I've chosen here, I just have 3 register addresses sequentially: E0, E1, and E2. To get those register addresses, you have to refer to the user manual for our board to see what's being used and what's open. There's a large register space that's open on the board, and that's intended for users to access. So.
And you can grab our manual from our support page on our website as well. So that's something you can go download, and you'll know what those registers are that are available to you.
So up here we have we're declaring register address space for the LFSR. We have our control register, seed register, and data register. And in this module, we're not declaring the actual addresses that the XLR8 board is going to be using. We're just declaring that we need some register addresses for it. So we'll be setting those in another step. I'll point that out. And again, much like the test bench, we have our clock and reset values here that come into the XLR8 wrapper. We have a data bus input and data bus output for the wrapper, and all of our XLR8 blocks have these RAM access controls. So you input a RAM address, and if that RAM address matches one of the registers in your block, then your block knows that it needs to do something with that, with the address on the bus. Then there's a read enable and a write enable, so that's declaring when the user is expecting to be able to read or write from a register. And there's some control signals down here for the 3 different registers. So each of the registers has a select signal, a write enable, and a read enable signal, as well as a value for the register itself. So if the user is going to access one of those registers, it would be that access is controlled here. So again, there's LFSR control, LFSR seed, and LFSR data. And this is the implementation of the logic that, again, is looking for if the RAM address comes through and it matches the control address, it knows to do something with the control address. If it matches the seed address, it'll do something with that, and again for the data address. And down here we have a block. Blocks like this, you need something pretty much identical to this to control a write to a register. So that's why, so there's 2 blocks here. There's one for LFSR control and one for LFSR seed. There is not a write control block for LFSR data because that register is not writable by the user. And then down here we have the instantiation of the LFSR block itself. just like we saw in the test bench, we're inputting our local clock reset and our local values for enable, seed, and the LFSR data value.
So this is sort of the wrapper that prepares it to get pulled into the top level, right? So this is, and if you scroll up to the top quick and look at those parameters, I think that was you made that point, and we'll see these values show up, that these parameters, this is a sort of a unique data type in Verilog, that it's sort of like a constant that you set, that you can set either here in the code in this file, or you'll see that it can also be set or modified when this module actually gets instantiated in the next level. So it's sort of a unique method for setting what's effectively a constant within this particular Verilog file, or within this particular file for Verilog.
Right. Okay. Okay, and here, like I mentioned before, we have to define the actual address for those registers, and there's a file that if you're creating your own XB, you want to populate this XB address pack file, and this is really all there is to it, is just declaring your the addresses that you're going to be using. So there's the LFSR control address, the seed address, and the data address. And just like I said before, I'm using E0, E1, and E2 for those values. Okay, now that we've done that, we have the LFSR block itself that handles the logic for calculating the LFSR, and we have the XLR8 LFSR wrapper that handles communication between the XLR8 board and the LFSR block. Now our next step is we need to get that into XLR8 Top. So XLR8 Top always contains our XLR8 core components, and these are the components that make the XLR8 board behave as an Arduino board. So these core components are always there, and we're going to be dropping this XLR8 LFSR block into XLR8 Top along with these core components, so that XLR8 LFSR functions in tandem with these components.
And this drawing is not to scale. So I'm looking at the LFSR code is certainly not that much bigger than the ABR core itself. But we wanted to draw attention to it. I just had to chuckle when I looked at it by comparison to the core itself.
Right. Okay, so we'll get into XLR8 Top now, and this is mostly a step of instantiating the block itself and creating our local variables so that the XLR8 board is able to communicate with the LFSR block. So we'll take a look at that now. Here's XLR8 Top. When you get into XLR8 Top, there's an awful lot to see. This is the control for everything that the XLR8 board is doing. So there's a lot of wires in here declared. There's a lot that you could look at, but really, when you're implementing your own XBs, down here is where I've declared the control signals that I'm going to be using for the XLR8 LFSR block. So I have a slave data bus out and a slave out enable signal for the LFSR, and this is where communication happens between the LFSR block and XLR8 Top. So you need to declare those up there, and then I'll get down at the bottom of the file here. Again, there's an awful lot in here, but most of it won't be pertinent to you unless you start to get into really low-level parts of or low-level changes to the XLR8 board. So way down at the end of the module is where I have created my instantiation of the XLR8 LFSR, and here we go. This is where I'm setting the parameters for the XLR8 LFSR, and I'm feeding in those addresses that I declared in the address pack, I'm telling the LFSR module to use these addresses for register access. And then down here is where I'm putting in the core clock and the core reset. I'm just feeding in the clock signals from the Accelerate board, and I'm setting the communication signals that the Accelerate board uses for everything. So, and then right here, these are my signals that let the LFSR module know that the Accelerate board wants to talk to it. And then, yeah, up here, when you create a new module, you're going to have to modify this STGI XFIO slave dbus out and this slave out enable, and you want to put in your control signals, add those control signals into these signals, so that the Accelerate board knows when it needs to talk to the LFSR module. Okay, the next step before we get into actually compiling the design, we need to open up the Quartus QSF file. So this file is in the LFSR directory under the Quartus directory. So we can go ahead and show that here. So here we are in Accelerate build, and we go into extras, where here we've been working mostly in RTL. If we step into Quartus, this is where the QSF file lives. So this is where a lot of this is where all of the Quartus files live that actually let us compile, and so that it knows the setup of the directories and that sort of thing. So I've opened up Accelerate Top QSF, and here there's a section called XB RTL, and this is where you want to add, if you're creating your own XBs, you need to add the files that are relevant to your XBs here, so that Quartus knows to compile those in. So here we have the Alorium LFSR block, the Accelerate LFSR block, and the XB address pack. So those are the files that we've modified and added. So those need to be added into the QSF file, so that Quartus knows to compile those in, and the rest of the file stays unchanged. Okay, and we've gone over this step once before, but I just wanted to reiterate. For Quartus to be able to compile our XBs, we need to add in our core library. So I'll just show how to do that one more time. You go under Sketch in the Arduino IDE, go to your Include library, and you want to Manage Libraries. Okay, and you can, here in the search bar, if you just search for Accelerate, you end up with all of our libraries. And you need to get the core library, and the build template is what you get when you want to build your own XBs. So I have it installed already, but if you don't have it installed, you need it.
And to shed a little light on that too, so we keep talking about this Accelerate build directory, and if you remember back in the early, we had you download, or you would, as an example, if you want to start with this LFSR block, we downloaded the LFSR zip file, and then we moved it under our libraries, Arduino libraries, and renamed it to Accelerate build. And that Accelerate build template that he just showed, if you were to download and install that under libraries, you'd see Accelerate build template. And if you want to create your own XB completely from scratch, you would basically make a copy of that directory, but just take the template off the name, and it would just have the Accelerate build. But it populates a lot of the files and the things that you need to be able to start building your own custom XB. The value of starting with LFSR like we've done here, or if you wanted to use it as a starting place for you, literally everything is already there, right? So you could just change the name, the Accelerate build, and all these, the source code and the test bench and all that's there, so you can give it a try. and you can run it as is, and then you can start experimenting, which is making simple changes to it. Say you want to change the tap points on it, or maybe you want to add another configuration input, and slowly work your way toward making changes not only in the base RTL or the base source code for the file, but then make changes that'll impact modifications to the register interface and then give you additional features. So that's really what we wanted to do, but you still need to download the core and the build template, because it adds some things kind of under the hood that allows us to be able to do the programming with Arduino.
Right. Okay, and one more step that you need to make sure that you've done to be able to actually, so the Accelerate board works as an Uno board out of the box. You don't need to install anything extra to get that to work. But to be able to actually compile for using the OpenXLR8 flow, you need to have the OpenXLR8 board available to you through the Arduino IDE. So you can accomplish that by opening up or clicking on the Tools button up top, and then you go into Board and you select the Boards Manager. That'll bring up a search window. And again, you can search for Accelerate, and the Alorium Accelerate boards are available here. And again, I have it installed already, so I won't be doing anything. But if you haven't installed it, you need to install it here.
And this is where that URL, that other URL that Harley had posted in the chat window, becomes important. Just like standard Arduino boards, in the preferences for Arduino, you can list where Arduino can go and search for these additional board packages, and that's where you would use that URL. I think most of the people, based on the poll we did, have some experience doing that, so I think you've probably run through that before.
Right. Okay. Okay, so now we're all set up for it. We're going to get ready to actually synthesize the design. So we have Accelerate LFSR incorporated into our Accelerate Top, and we're going to send it through using Quartus Prime, the Quartus Prime tool. We're going to create an RPD FPGA image file that we can then write to the board. And one thing that we could do, we have the capability to load the full design into ModelSim, so you'd actually be able to see all of the signals available to Accelerate Top, and you'd be able to create your own test bench to stimulate Accelerate Top, but we're not going to be doing that today. I open up Quartus Prime, the Quartus Prime tool here, and we want to, under File, we want to open our project. Okay, and to find our project, again, we go into the Arduino libraries area where Accelerate Build lives. Happens to be a favorite of mine here already, but if you go into your documents, this is where Arduino installs things by default. So we go into Arduino, go into the libraries, and we've been working in this Accelerate Build directory. And then we go into the extras and into Quartus, and we find the Accelerate Top QPF file, the Quartus project file, and open that. And this will take a moment.
And what is the QPF file doing? I mean, in terms of what's the value for our users because we've already got that all set up?
Yep. So the QPF file has, we have a lot of instructions already sort of pre-made into it that tells it where to look for Accelerate Top, tells it where to find the QSF files, and where to find Accelerate Core, everything that it needs to fully compile our design. So I've loaded in the design now, and it's ready to go. Now you can go into processing and start the compilation. This is going to fully compile the design, everything that we've been working on, all of the LFSR, Accelerate LFSR, and the address packs, and all of our changes will be compiled together. Now I'm not going to go through this step today because it takes a while. Depending on your hardware, it could take from 5 minutes to 15 or 20 minutes. It's a fairly large process, so So I already have this design pre-compiled, but yeah, that's the steps to go through. Is you go to processing and start compilation. So after compilation is completed, you have a compiled Quartus project file. Now we go to File and Convert Programming Files, and that we can see here down under File, Convert Programming Files. Then we want to click on this Open Conversion Setup Data, and again, we're under the libraries Accelerate, Build, Extras, and Quartus. There's an OpenXLR8 COF file that we want to double click on. And yeah, this happens to be for an older version of Quartus, but that's no problem. So this COF file, we have our compiled version of the XLR8 Top. So now we need to tell it to build into a format that the Max 10 on the Accelerate board knows how to, the format that it knows how to run. So, so after we've loaded that, we just click on Generate. And it already exists. I've done this before, so I'm overwriting some files. The RPD file already exists. That's fine. Okay, so after I hit Generate, it has generated the output successfully, and we can close out of that. Okay, so at this point, we've gone through Quartus. We actually have the image file ready to go. It's ready to be burned onto the Accelerate board.
And the step we just went through, Brian, right, is to really prepare the output of synthesis in a format that we can load using IDE and the sort of the methodology that we put together, right?
Right, yep, we're going to be able to now load this image file through the Arduino IDE onto the Accelerate board. Okay, so, and that's our next step, is to put that RPD image file onto the Accelerate board. So go ahead and bring up the Arduino IDE. And under Tools, you need to make sure that your board is set to OpenXLR8, which we went and got that board available to us. There's the Accelerate Revision 2 available and the OpenXLR8 board. What we want right now is the OpenXLR8 board. That by selecting that board, the Arduino IDE knows to look for the fully compiled RPD image file under that Accelerate build directory.
And for those who aren't familiar with Accelerate, the Accelerate Rev 2 option that's under there, that's just the standard default. So if you bought a board, an Accelerate board from us, and you wanted to plug it in and just start using it, that's the option you would select. And then it's going to treat it just like a normal Arduino clone, or it'll talk to it with the IDE, but that's the default. We really only need that OpenXLR8 option when trying to load something unique, as Brian said.
Right. Okay, and last thing to check, just make sure that your Accelerate board is selected under your port. Mine is. It happens to be COM4 plugged into the USB here. And once all of your settings are set up, you can click on this Burn bootloader down at the bottom, and it's actually going to grab that RPD image file and burn it to the board. So I'm going to go ahead and do that now. And this is a process that takes a couple minutes to do. You can see I've got the output turned up to high on the Arduino IDE, so you can see it going through the steps, writing that RPD image to the Accelerate board.
And this is the step that a lot of people, this is really pretty cool, is to be able to upload and actually change what's living on the configurable hardware of the FPGA just using Arduino in terms of loading it is really valuable, because it doesn't require that you purchase additional hardware or any other module to be able to program it. So that's really cool. And I'll make the comment also that when Brian was stepping through stuff with Quartus Prime, it again, just like I said with ModelSim, there's a lot going on, and even the step of converting the file, it's kind of multiple windows and buttons and all kinds of options, and we've tried to make it clear just step by step what you need to do without trying to describe what everything is doing, because there's so much going on in that tool. But kudos to Altera and to Intel for the tool that they've got and that they make available. What you can do with Quartus Prime for free and the power it gives to create these designs is really quite phenomenal. So there's a lot happening there, and it's don't let it again spook you guys. We try to lay out as much as we can. If anything isn't clear with the instructions, or you want to give feedback because it could just be make more sense, hey, do this, let us know, because we want, over time, we're going to continue to refine this flow and try to make it easier and easier for our users to navigate these tools. We know there's a lot there, so your feedback is very, very welcome in that regard.
Okay, now I've gotten this message. This is really all the fanfare that Arduino IDE gives you. It just says done burning bootloader. So that's completed successfully. So our next step is going to be to try it out, see if our communication is working. So we have this FPGA image burned now that has a hardware LFSR on it. So I have this, I'll bring this up next, this Accelerate LFSR communication module. And this LFSR example is it's a part of the Accelerate LFSR that you would have downloaded to go through this process. So here we can see this is my Accelerate LFSR header file, and here I have these pound defines for memory access. This is telling the Arduino software where the registers that I've created exist. So again, I have this LFSR control, seed, and data register, and I'm telling it the addresses are at E0, E1, and E2. So this matches exactly what we created in the RTL. And I have a few functions that I've defined here for access. So I have this function to set the seed, and all that's doing is taking a user input of a seed and setting it to the Accelerate seed register. I have this get LFSR, which is just returning the value held at the Accelerate LFSR data register, and set free running mode, and that takes in a Boolean and just sets that that single bit to the control register to enable free running mode or not. And that's really all there is to it. And here we have this. This is my example code here. So in setup, I'm turning on serial communication so that we can see the output. I'm setting the initial seed, and I'm telling it. In this instance, I'm telling free running mode to be false, so I'm not turning on free running mode. And then down in the loop, I am just continuously saying get the LFSR value and print it to the screen, and then wait for a second. So let's go ahead and run that now. I'll upload that to the board. Okay, and we're done uploading. Let's pull up a serial monitor, and it takes just a moment. And okay, and after reset, we start to see that the LFSR starts outputting to the screen. So this, again, I've got it set in binary mode so you can kind of see what's happening. But it's grabbing the lower 7 bits and performing that LFSR calculation on it and appending the single feedback bit to the end and printing it to the screen. And since I've set not to be in free running mode, it's going to only update the LFSR every time I read back from it. Just as an example, we're going to set free running mode to true now. So now the LFSR is going to update as fast as the clock will allow it. So I'm still only going to be reading the LFSR about once every second. And we can see now it's pretty much, it looks random. It's not something that you can follow along with anymore. And as one more illustration, I'm going to set this to output in decimal.
And going back while this is compiling to your point, Brian, about whether it's free running or whether it only advances every time you read it, think again for if you're looking to generate a pseudo-random yet predictable string of numbers for one reason or the other, it is really powerful or valuable to be able to just only have it advance to the next number every time you read it,
Right.
because you know the sequence of the numbers you're going to get. But when it's free running, you may not access that register on the same interval every time you run a simulation or every time you use it for something. So you truly will get what appears to be a random set of numbers based on a given seed. But that's a really useful thing for being able to recreate scenarios or recreate the same sequence in the background. And if you're trying to isolate some kind of failure or isolate something with sort of this pseudo-random testing.
Right. So this is kind of our final output. This is what we've been working to. We have an 8-bit LFSR that is running in free running mode now, so it's updating faster than a human's going to be able to keep up with it, and it's just printing out to the screen. It's unpredictable. This is our 8-bit random number. Okay, so kind of my illustration now, if you remember at the beginning, we were talking about the compiled assembly code of the software version of the LFSR. So every time the LFSR updated, it had to step through this sequence of assembly code instructions. And now we can see with the changes we've made, we're just calling hooks into the FPGA essentially. We're just accessing registers. So here on the right side, this is the assembly code compiled that for advancing the LFSR. Up here on the top, this is the code to set the seed. So this is being called once initially when the program is set up. And then down on the bottom, this is the code being called to get the value of the LFSR. So really, every time the LFSR advances, we're just calling these two instructions on the bottom. So, I mean, this is a very, very simple example. The 8-bit LFSR is not a very ambitious program, but if you imagine, then you have the more complicated your software is that you're trying to replace. Turning that software into FPGA code, the returns on it are much greater.
And certainly, as you said, I mean, you get into some real complex software code, and it is not necessarily trivial to unroll that into hardware. But very often it can be done, and there are certain types of functions that are really are good candidates for moving into hardware, and that can just kind of stand and run on its own. But I think the value of this and this illustration that Brian showed is just a really great example of the offload capabilities of pushing this out and allowing it to run out there. So imagine this instead of being just an LFSR generator, but imagine you've got some kind of sensor monitor that you want to be paying attention to, and it's something that you may or may not want to do something with the data coming back from that sensor. But if you have some array of sensors, you can have these little engines hanging out in the FPGA just monitoring that thing, and it'll only interrupt or bother the CPU if it needs to, by setting some kind of interrupt or setting a bit, and the CPU can just kind of be doing its own thing and doesn't have to do this. So imagine if you had multiple of these LFSR blocks running, or you needed to want to keep multiples of this going. The resulting impact of being able to run it in hardware is really valuable to allowing you to do other things with this board. So this is a great example, Brian, of being able to shrink that down.
Okay, and yep, thanks everybody for joining us today. I hope that this was valuable to you.
Yeah, and we've got some time here to answer any questions. We didn't have lots of questions come through as we've been talking. I had a few that we've responded to, but do want to say if there are things you want to ask, now's a great time. Go ahead and type them in the Q&A window. We can answer those. We will hang around for a little bit, but that is the end of what we wanted to present to you formally. We covered a lot of ground when you think of starting from here's a simple block, to simulating that or looking at that code, simulating it by itself, wrapping it in its own wrapper, putting it in the top, running that through synthesis, introducing the code, loading it to the Accelerate board, and then running it. That's a lot of ground to cover in about 90 minutes or so. So I would not be surprised, and we wouldn't be surprised if you're thinking, I don't know if I could go back and necessarily replicate this on my own. But if you have questions, now's a good time. Go ahead and you can hit us through our website at aloriumtech.com. We've got a forum there. We've also just got direct ways to contact us. We want your feedback. We want to make this easier to use, but we think it's a really great way to get started putting your own FPGA code onto a board that you can use in a really familiar environment and program with the Arduino IDE. Some of the questions we're getting that I got now is like, where's a good place to start? And are there examples to highlight some of the basic models and some of the basic things? And I think, Benton, if what you're asking is what are some good blocks to use as a starting place for an Accelerate block? And I think that I would recommend maybe you just start with this LFSR circuit, because it's pretty straightforward and it's pretty small. And even as you saw the example code there with the Arduino sketch, it's pretty simple. There's not much for inputs into the block. There's essentially, you can set that free running mode to true or false, and you can just run it really simply. And if you start there, you can scroll way into that LFSR.v code and look at that and be able to say, okay, well, here's how it works now. I want to make a couple changes. So instead of tapping off these points, I'm going to pull up different tap points. Or even a simple place, if it's your very first time using some VHD or writing Verilog, just set it to always be output a 0 or output some fixed value, and then run through the process and run the sketch. So then everything else would stay the same, but then the output you would see should be 0, right? And you'd be able to see that, okay, I made a change in the Verilog, and that change replicated through all the way to when I ran it on the sketch. And it'll allow you to slowly start just making tweaks and changes. But this LFSR block is a pretty good place to start. Basically, any of the XBs that you download. So when Brian brought up the Arduino window, and actually, Brian, maybe you could do that, bring up like a folder that shows all of our Accelerate libraries. I think that you can go in on most of those, I believe. If you can't now, you should be able to, and we'll make sure we can down the road. But you can go and look at those. So if okay, I want to do my own servo block or something like that, you can take a look at how we implemented Accelerate Servo, and you can copy that over for your Accelerate build library, your Accelerate build folder, and you can use that code as an example, as a starting place.
I'll jump in here and mention that I don't believe every one of our Accelerate blocks has the full Quartus structure behind it. I know that the LFSR block does, as we've shown today. The servo library also does, and I believe the 3 SPI pins that we have also does. I'll check. Yeah, it looks like the float XB does not have all of the infrastructure available for it. But yeah, those 3 are fully available. The LFSR, the servo, and the 3 SPI interfaces are fully available on our GitHub repositories.
Well, if nobody else has any questions, I just want to, oh great, Ben, so it sounds like we answered your question, so that's great. And thank you everybody so much for being here this afternoon. This is our first time doing this as a webinar, and so there's no doubt that you sort of had to, come through maybe some of the clunkiness that we'll clean up in later times. So thanks for hanging in there with us. A handful of names that I recognize here that are visiting with us today and on this call. Thank you so much for your continued support, for using Accelerate, and we're just really excited about the capabilities this might bring you in whatever projects you're doing at work, and some of our educator friends that are out there. So go ahead and stay in touch with us. Tell us how we can help you, and we want to make sure we're enabling this platform to be as useful as we can as it goes forward. All right, guys, I think that is it for today. We're going to go ahead and shut things down. Thank you, Brian. Thank you, Harley, for running infrastructure in the background. Appreciate it. And we'll keep everybody posted on what's happening next. If you haven't joined our email list yet, you can do that. Go to loriumtech.com, just about any page will give you that option. We aren't going to pester you too much, but we'll keep you posted on some things we're doing, and we've got some new things we're going to be introducing and announcing very soon, so keep your eyes there. We look forward to interacting more with you in the future. Have a great afternoon, and we'll talk with you again soon.